about S matrix for massless particles.
First, I would like to thank the organizers for inviting me to this very enjoyable workshop. And today, I'll talk about the S matrix for massless particles based on this works with Freddy Patricia, and his student Alice Smith here in the summer. So. For the past 25 years, basically, it has become clear that the S matrix of massless particles is something very special. So the beginning of the story starts with some work Park and Taylor and other pioneers did in the late 80s. That the work of them lead to a remarkable fact that if you consider scattering 2 gluons into n-2 gluons, all of them with positive helicity, naively you can write down thousands or millions of terms of Feynman diagrams, but the final answer is the simplest thing you can imagine. It's just a one-line, famous Park-Taylor formula. So this has clearly indicated that you know, the scattering amplitudes. We should think of scattering amplitudes in some other way, rather than just write down the Lagrangian and compute the S matrix from Feynman diagrams. So just like the holography is the religion of Diego, this is like the religion for amplitude people. That there is some dual description of the S matrix quantum field theory that is will manifest the simplicity and all these remarkable structures discovered in the final answer without passing through all the Feynman diagram calculations. And this dual description should tell us more about the fundamental theories of our nature. So here's the plan. Now, so basically, the story I will present is the newest addition to this line of thinking. That we found a formula, strikingly compact formula for this tree-level S matrix of massless particles in arbitrary dimension for all the spin 0, 1, and 2. So I'll discuss the formulas in 2 parts. One is the so-called kinematic part, which is independent of any theories. So as long as you consider scattering of massless particles, these so-called scattering equations will appear as a basic setting for the description. And then I'll go to the second part, which is the dynamical part. If you give me a theory, like Yamil's or phi cube theory or gravity, I'll write down, based on the scattering equation, I'll write down some content of the formula which will exactly produce these things. And more than that, it will give you some properties, as I said, some nice structures of the S matrix, which is completely obscured by the Feynman diagram. So this will be the third part. If I have time, I'll go to that. Going to show that these new formulas manifest many nice properties of the S matrix of massless particles. So yeah, the more recent interesting trigger is 10 years. Basically, exactly 10 years ago, started with Wheaton's observation that the tree-level scattering, at least the tree-level scattering amplitudes of n equals 4 super μs in 4 dimensions, can be given by considering a string theory whose target space is the twistor space. So this twistor string theory, although it didn't really generalize to all the loop level, it triggered a huge amount of research activities, especially for n equals 4 super μs and also for other scattering amplitude in other quantum field theory. So maybe some of them you're familiar with, like recursion relations such as the BCFW and also CSW recursion relation. They've become very valuable tools for computing amplitudes. But there are also some other more direct consequence of Wheaton's twistor string theory rather than these recursion relations. There are these so-called twistor string inspired formulas for the tree-level amplitude. For example, the earliest one is given in Wheaton's paper in twistor space and then translated to the momentum space by Roy van Spratling and Volovich, now as RSV Wheaton formula, which is a very compact formula written as integral over the moduli space of certain rational map from the CP1 to the target space. They give all the tree level S matrix of the n equals 4 superior mules in a very, very nice way. And last year there are some generalization of the story, finally to gravity, in particular to n equals a supergravity, that you can also write their tree level scattering amplitudes in a similar fashion. So there exists twistor-string theories also for the S matrix of supergravity. And also by Sami and Yuting, there's this nice story, similar formula for three-dimensional theories, especially for ABJM theory, that there is this formula behind the tree level scattering amplitudes. So a very natural question is to ask, I mean, is this just a coincidence when you have nice kinematic simplifications in 4D and in 3D, and also with all this supersymmetry, or is there a more general story behind it? So that's also applied to the recent progresses. I mean, one of the highlights of the past few years is this so-called Grassmannian approach, or this leading to this very recent understanding of amplitude hedron for n equals 4 superior mules, but to all loop level. So this is a very nice story that basically realize this goal, saying that we have a dual theory for the all loop S matrix of some very special theory. But you might wonder, I mean, is it just due to integrability or due to this theory is so special? Are all this simplicity also behind the S matrix of other theories? So in this talk, I'm trying to answer this question. At least for the massless particles, I'll give an affirmative answer that such formula do exist. So
that formula relies on supersymmetry?
No, it's a for any massless particle with these spins, you have such a very similar formula. So basically, no supersymmetry.
And you allow arbitrary higher derivative terms?
No, just for Yang-Mills gravity, not. I mean, you could imagine generalization of this formula with higher derivative terms, but now I'm just talking about the simplest formula. So as I said, there will be kinematic part and dynamic part. So basically, the idea is I want to build a map from the sphere with n punctures to the kinematic space of n massless particles. So given n external momentum, each of them is massless, and the momentum should be conserved. I want to see if I can describe the same physical content in an alternative space, which is a space with n puncture, which is a sphere with n punctures labeled by this positions of puncture and complex number. So I'll claim that for any massless scattering of any massless particles, you will find that it's very natural to describe all the kinematics by some equations for these variables, given the positions of this punctures will be constrained by the external kinematics. So this is a so-called scattering equation, which is very general. And then the scattering amplitude will be written as an integral over the moduli space of such puncture spheres on the support of these scattering equations. So the next step in the dynamical part is just you try to find the correct integrand of such an integral formula, which will reproduce the theories you want. And by doing so, lots of properties become manifest. For example, in Feynman diagrams, each diagram is not gauge invariant, but here you will see that the formula is manifestly gauge invariant for particles with spin. And also this very interesting story for the past few years, there's some duality between color and kinematics for gauge theory, and how it got squared into gravity. So the basic idea of gravity amplitude is actually the square of gauge theory amplitude due to BCJ, and goes as early as this KLT relation between open and closed string. They will all become manifest in this new formalism.
So it's only on shell amplitudes?
Yes, yes. Okay, so basically out of time. I'll try to be very quick. So the thing, the basic idea is I want to have a map from the sphere to the light cone of my d-dimensional momentum space. So this is I want to have a polynomial whose I want to have a polynomial map from the sphere to the momentum space, which will satisfy this null condition for each point on the sphere. And you can easily see that the easiest way to realize this. So this is a very, very interesting thing to realize, that if you want to map each puncture on your sphere to your external data, you have no choice but to have a degree n-2 polynomial, because this is the only way to realize momentum conservation. So if your external kinematics, external momentum satisfy conservation, this is reflected through this map by a residue theorem that you sum over all the poles you have in your rational map, which in turn becomes the negative, the pole at infinity. So for this to vanish, you have to have a degree n-2 map. So this is the starting point. And then we require this map to be null, not only for this n punctures, but actually for any point on the sphere. So this is our starting point. You want to map it to a light cone. For any point on the sphere, you want the square of your image to be 0. So this actually requires not only these n equations, which are guaranteed by the on-shellness of your external momenta, but also the derivatives at this n puncture. So this gives you, in turn, a very simple set of equations that we call scattering equations. So they are the backbone for your scattering of any massless particle. So given these Mandelstam variables, from the kinematic invariance formed by your external data, we have n such equations. For each particle, you have this particular combination give you 0. So these are the constraints we put on your sigmas given by external data, such that there exists a map from sphere to the light cone. So this will be the most important ingredient of the story. And there are some nice property for the equations, such that they satisfy SL2C symmetry. So you're on a sphere. So 3 of the punctures are actually redundant. You can use the SL2C symmetry to fix that. But also, out of the n equations, only n-3 of them are linearly independent. So actually, you can fix the SL2C symmetry by eliminating 3 variables and also 3 equations. So if you look at these equations, as I said, they are labeled by this a from 1 to n, but actually only n-3 of them are independent. So these are some examples for what the equation really looks like at 4 and 5 point. You can see that 4 point is a linear equation for 1 variable, which you can choose to be the cross ratio by fixing particle 1, 2, 3. And for 5 point, there are 2 equations labeled by a equals 4 and 5. Both of them are quadratic, and for these 2 variables, R4 and R5. So this equation just gets more and more complicated. I mean, although they look very simple, if you want to really write down all of them for higher points, say for 6 point, you'll find 3 equations. Each of them is actually degree 6 polynomial equations. So the point is that you need to solve all such polynomial equations. Then the amplitude is given by sum over the solutions of them. But these equations are very interesting because they know the factorization of your amplitude. So the most important property we want to have here, at least for tree-level scattering, is that your amplitude should only have physical poles when your kinematic invariance goes on shell. And on each of the physical poles, it should have the correct residue, namely the residue is given by the products of 2 sub-amplitudes. This is the reflection of the locality and unitarity. So now we are away from Feynman diagrams. These 2 properties are not guaranteed. So the most important thing is that in such a dual formulation, you want to see the locality and the unitarity through these equations. So I'll show you how to see them. The relation is that when you send some kinematic invariance on shell, the equation actually factorizes into 2 sets of equations. So your system is basically become 2 subsystems, and it's very easy to see that the equation also become decoupled. So basically, if you have a sphere from the beginning with n punctures, and when you send some kinematic invariance on shell, you expect the factorization of your system. And the equation does the job by saying that the sphere becomes 2 spheres. with these two systems, and on each of them, you have a scattering equation for the subsystem. So in some sense, it knows the factorization, so it has a very good chance of describing the tree-level scattering. And I would like also to mention that, as I said, you can actually solve these equations, and that's the point, right? We want to write the amplitude as integral formulas on the support of the equation, which in the end turns out to summing over all the solutions. So there are n-3 scattering equations, and the number of solutions for them is actually the n-3 factorial. This can be also proved using the soft limit of the system, that when you take one momentum becomes soft, the system basically becomes the system with n-1 particles, and then when you try to solve the last one, you can see that you get this number of solutions. And this is in practice how we solve the equations.
So where do you find the information on the spin of the particle?
This is the kinematic part, which has nothing to do with spin or it's just kinematics. I'm giving you the n momentum. You give me back the positions on the sphere, and then in the second part, the formula, the content of formula will be the theory specified.
What about infrared divergences? You took the soft limit. So what about infrared divergences?
No, yeah. So I'll show you that the formula will reflect all this soft behavior.
So it will have some infrared.
Yes, it will have the correct soft behavior.
Okay.
So here it's just kinematic.
Okay.
So how do we use this equation? As I said, it's just summing over the solution. So we write down the standard measure of this m integration over this n punctures, and we insert the scattering equations. Of course, here you need to exclude 3 of them to make sure that you only insert the linearly independent ones. And this becomes the final formula, that we really want to find an integrand that depends on the sigmas, and possibly also on the, for particles with spin, it will also depend on polarization and so on, other kinematic invariants. And then we want to integrate over the sigma on the support of this equation, which turns out to be just summing over the n-3 factorial solution, that you solve this equation, you obtain them, with a Jacobian. And the integrand and Jacobian will be evaluated on this solution. And the Jacobian turns out to be something very nice. It's a permutation invariant object coming from the determinant with columns and rows deleted, reflecting the SL2C invariant. Okay, so much about the kinematic part. How do we get the amplitude? We just want to find the correct integrand for different theories. And the simplest case we found is, okay, first of all, the integrand must transform under SL2C with a certain weight to make the formula meaningful. And also, it should give all the physical singularity and the residues. These are all requirements for the integrand. And actually, you will find that there aren't so many choices. So give me a theory, I can give you the integrand. Okay, the simplest possible thing you can think of to satisfy such a transformation and have the correct physical pole is actually these so-called Park-Taylor factors on the worksheet. You take the difference of adjacent punctures, and this is what I define as Park-Taylor factor, and you need to square them to get the correct weight. And what if you just take the sum over solutions on this simple integrand? The answer turns out to be something very nice. It's exactly summing over the cubic diagrams in this particular ordering that you pick with all the propagated. So what is it? It's a amplitude for the phi cube theory. This is the Feynman diagram, summing over Feynman diagram. So this simple formula, as summing over the solutions with this integrand, gives you the amplitude for phi cube theory. Okay? So let's go further. Slightly more interesting. What if I take 2 copies of Park-Taylor with different ordering? I mean, this is allowed. This is allowed has the correct SL2C weight and so on. And I sum over the solutions with the Jacobian. This turns out to give me the summing over cubic diagrams that are both consistent with ordering alpha and beta. And what are they? They are actually some basic ingredients for phi cube theory with 2 gauge groups. So this is the most natural generalization of the simplest phi cube theory, which is phi cube theory colored under 2 gauge groups with this interaction vertices. So if you summing over the Feynman diagram for this guy, you'll find that it's given by summing over pairs of scatterings with color factors, and this is so-called the double partial amplitudes that is given by our formula. So to summarize, the simplest integrand you can think of is given by products of such Park-Taylor factors. And they give you all the amplitude for phi cube theories. So basically, later I will show you how such a summing over solution on this integrand and this summing over Feynman diagrams, they are the same rational function. So they have the same poles and residues. But let's move on. So what about theories with spin? Of course, now the integrand will depend on not only just sigmas, but also say the polarization of your particles. And now, what's your guiding principle? So for example, for Yang-Mills, you can imagine that you still keep one copy of the Park-Taylor because it's colored under one gauge rule, say UN. But what about the other copy? What is your basic principle here? It's gauge invariance. So I want the integrand itself to be some nice function that when I do a gauge transformation, it will remain invariant. So this is something very non-trivial, that if you write down Feynman diagrams, each of them is not gauge invariant in general. But our formula will give you such a nice behavior on each solution. So basically, this is the simplest possibility we found, and turns out to give you the right Yang-Mills amplitude. So what is it? We want such a matrix, antisymmetric matrix that's built with these blocks, such that it's very easy to see that if you replace polarization by its momentum, this matrix will have two column and row coincide with each other. So you can see that this part becomes this part, and this will become this part. And also, that is only true on the support of scattering equations, because you want the diagonal part here, when you plug in epsilon A, it becomes Ka to be 0, which is the content of the scattering equation. So this is basically the only thing you can write down to have the correct SL2 weight, and also to be gauge invariant on the support of scattering equation. And it turns out it's the correct integrand. So if you do this measure with the Park-Taylor I just defined under one copy of the UN, and you take in the Pfaffian of this matrix, you find it gives you the correct amplitude for Yang-Mills. So this is the definition of this reduced Pfaffian that coming from this matrix. Okay, so what about gravity? Of course, you can imagine that now you don't need color, so you can get rid of the Park-Taylor piece. But now you have polarization tensors, which are basically like two copies of the polarization vector. So this is the most natural thing, that instead of a color copy and a Pfaffian, you take two Pfaffians. The product of two Pfaffians with polarization vector epsilon and epsilon 2. And this turns out to be the correct formula for the gravity amplitude, I mean, including dilaton and action, because you can have, in general, two different polarization vectors. If you specify yourself to the traceless symmetric component, then one way to do it is to choose this epsilon and epsilon tilde to be the same. So you get the Pfaffian squared, which is a determinant. So this is the formula for all this complicated scattering of gravitons. You just sum it over the solutions of scattering equation with this Jacobian, and then you take the determinant of the matrix I just told you with this polarization vectors and so on. So this, you can summarize the formulas for massless scalar gluons and graviton in this way. That you have some power of this color factor, Park-Taylor kind of factor, and some power of the polarization dependent factor depending on your spin. So all the formulas, all the three formulas can be summarized this way.
So what happened for other spin 3, 4, 5, 6?
Okay, you can try, right? If you plug in spin 3, you would have color factor in the denominator. Or if you go to spin negative, you would have polarization in the denominator. So they are all impossible. So this actually gives you a range of the spin that's consistent. Also, you can see soft limits, like in one line. Basically, as I said, the scattering equation itself becomes, in the soft limit, it becomes the n-1 particle system, and then the equation for the last particle. So basically, you need to get the n-1 point integrand, and then summing over the solution for the last sigma. And then under the soft limit, your far field also decomposing to the n-1 particle far field with a soft factor for the far field, which is the Cn, this factor that I wrote down on the slides before. So in the end, in the soft limit, your amplitude just becomes the n-1 particle amplitude with this soft factor being summed over the solution for this guy, which is, of course, nothing but the soft theorem. So we actually have an interpretation of the soft factor of amplitude as coming from the soft factor of this far field with the residue theorem, and same for gravity. And also you can study factorization. That's actually the most important check for us, that under a factorization, not only your scattering equation, the kinematic part factorizes, but all your Park-Taylor and Fabian, they factorize into the left and right part. So in the end, your amplitude has only the physical poles, single poles, as the kinematic invariance go on shell, with the correct residue. So this proves all the formulas we have. And of course, I won't have time for this. I'll just very briefly mention that if you know about BCJ and KLT, those are the relations between gravity amplitude and Yang-Mills amplitude. They all become manifest in this formalism. Because as you can see already here, that our formula actually has some sort of color kinematics duality contained in itself. This is the scalar field, and this is scalar amplitude and Yang-Mills amplitude and gravity amplitude. All you are doing is for each solution of your scattering equation, you replace the color by Fabian, and you do it again, you get gravity. So there is some relation between color and kinematics here. And you can do it more explicitly, that you can actually prove that your Fabian, just like your color part, can be expanded into this Park-Taylor factor as well. As I showed before, two such Park-Taylor factor will give you something over cubic diagrams. That means both for all your amplitude with scalar or Yang-Mills or gravity, you always get something over cubic diagrams with propagators, but only difference is whether you have two copy of color or a copy of color and the numerator, kinematic numerator, or maybe two copy of numerator for gravity. So this is precisely the statement of the BCJ, that there's a duality between color and kinematics, and gravity is the square of Yang-Mills amplitude. Okay, and you can reproduce all the 3 and 4D formulas, including the ABJM one, using this scattering equation when they reduce to this low dimension. And I just want to say as a summary that these formulas, they have very nice properties, and they of course they remind us of the amplitude in string theory, because these are the theories that you obtain when you take the field theory limit of your string amplitude. But it's not, it's different. So if you just directly take the alpha prime goes to 0 limit of your string answer, what you get is Feynman diagrams. Your worldsheet become this infinitely thin cubes, become this tree-like object, which is something over Feynman diagram. However, here, as I said, the sphere is always there. So it looks like a string theory formula. It looks like a correlator because the sphere is always there. But you only fix the positions of the punctures on the sphere by solving the scattering equation. So it provides a dual formulation of Feynman diagrams for these particles. And it still remains unclear to what are the relations to the string amplitude, in particular in the high energy scattering, that actually these equations become the Grossman saddle point equation in the high energy limit. So what are those relations? It's actually a very important open question. Also, we haven't considered in general how to couple to fermions and massive particles. And the general goal of this project is that you want to find a reformulation giving any interaction vertices, that you want to rewrite them on your worldsheet, on this sphere. And of course, you want to generalize it to loop level for Yang-Mills theories and gravity to see more of the properties. Thank you.
So I may be lost at some point. How do you distinguish the 3-point and 4-point contributions in terms of vertices?
Oh, here everything is cubic interaction.
Right, so how do you incorporate 4-point?
That's an open question. That's a very important thing. And you don't see the
and the gravity, you have 4-point.
No, sorry. What I mean is that you can rewrite Yang-Mills and gravity amplitude only in terms of 3-point vertices. This is, say, from this BCJ representation. You write them as summing over cubic diagrams with appropriate numerators. They are like dissolving this higher point interaction vertices into only cubic ones.
I'm saying the contact terms.
Yes. So, yes, they are contained in this new way of writing things.
Okay.
Yes.
Any other questions?
Maybe sort of applying your idea to the different amplitudes in ADS space.
No.
In the sense of self-bounded representation.
Yes, that would be very interesting. I mean, one thing important is actually you need, say, for phi cube theory, you need to incorporate the mass to reproduce some correlators in ADS space. Those mass will be the weight of the operators.
There's also higher energy scattering. The scattering equation simplified either.
Yes. So I don't have time to go there, but if you study this equation also applies to string amplitude themselves. So at finite alpha prime, you can use this scattering equations there. But in particular, the simple thing happens when you take alpha prime to infinity. Now, on top of this scattering equation, you also have the saddle point equations, and they are actually identical to each other. So in some sense, you get orthogonality applied at the high energy scattering of strings. Yeah.
So what
People
also,
identify this, have people identified algebra from the numerator?
Sorry?
Have people identified algebra suggested by the numerator?
Yes, like in this paper I mentioned by Donald and Ricardo, they're trying to do this explicitly see the kinematic algebra from our formula. Because we have shown that our formula gives you the BCJ satisfying representation. So you would like to see more explicitly the numerator coming from the formula satisfy the algebra dual to the color ones. The kinematics. Well, they only did it for self-dual sector at the moment, actually. There hasn't been, yeah, but that's some work in progress, I guess, for them.
Okay, so let's start again.